Hello, my name is Steve Bauman. I'm a licensed professional geologist. I don't usually do videos like these, but there's been this flat earth push out there lately, and they're not all pose, and they're not all just haha fooled you people. Some of these people are dead serious. And, you know, when you start talking about the earth, you're entering my area of expertise. So if you're going to spout a bunch of junk, I'm going to call you on it. Okay, so I decided to make this video not for the flat earthers, because I could drag them into space kicking and screaming and they would still deny that the earth is not flat. But video is more for the people who might be entertaining the idea of a flat earth and may think it sounds good but don't know the history or motivation behind it. And I'm not going to get into any of that. I was going to sit here spending a lot of time bashing flat earthers, but they do a pretty good job of that themselves, because most of them are desk jockeys. They sit there and they run a bunch of equations that sit there and try to fit their preconceived bias but don't match any actual observation. You know, I mean, if I'm trying to figure out the volume of a cylindrical silo with a dome half hemisphere, or with a dome hemisphere top, running the equations for cubes and pyramids isn't going to do me any good. I might get real numbers out, but it doesn't reflect reality, and that's what flat earthers try to do. Your equations don't mean shit if they don't fit the observation and testable experiments, okay? So this is an experiment I ran on May 14th, 2016. It was totally impromptu, so I apologize for the quality of the photos that I am going to include. But anyway, let's get started. Okay, so where I conducted my experiment was in the Upper Peninsula of Michigan. Okay, this is a good chunk, almost all of the Upper Peninsula. This yellow circle here, this point, is where I was standing. Now I'm going to get into how I know all this in a minute, but I just want to give you a point of reference. This is Lake Superior. Okay, these other points up here, these are well locations and outcrop locations for something totally different project. But so I just wanted to give you a reference of where I was. Okay, this is zoomed in. Now I conducted my experiment along Keweenaw Bay because this is a good place to do this. You have a relatively small bay with things that can easily be seen across it if you have right conditions. So this is a good place to do that. Now, especially since this jutting out peninsula, I forget the actual name, I'm just going to refer to it as the jutting out peninsula. The 4-mile mark from where I was standing is roughly, I think, right about here. So on a flat earth or round earth model, I should be able to see the shore. And that gives me good reference points and you know, good control points. Okay, so here's is even closer. Like I said, here's Keweenaw Bay. Here's that jutting out peninsula. Here's my actual location on that date. Now, just try to get familiar with this shape here. This and the peninsula, and this comes out this way. This part right here is going to be key. Okay. I was in Baraga. I was just north of the town of Baraga in Baraga County when I shot this. I actually was heading back from Houghton, heading south, and I actually stopped and turned around to do this because I realized I had an ideal atmospheric conditions to do this at the time. And I've actually this experiment has actually crossed my mind, but this one day I had it. So I figured I'd stop, and I had all my equipment because I was already out in the field taking other measurements. So I thought I would stop and actually run this experiment. Okay, here's the GPS coordinate that I got from my handheld GPS receiver. I got north 46.84743 by west 88.48. Okay, which placed me about right here. I was actually parked more over here, and when I conducted the experiment, I was along the roadway. So my GPS was off a little, But this scale right here says this entire bar right here is 146 feet. So from where I actually was to where my GPS put me at was about 60 feet. And I'm going to be shooting azimuths over miles. So that 60 feet isn't going to make much of a difference. But just in case you don't believe that that was my actual field GPS and I just plotted that on here to strengthen my point of argument, well, here's my handheld GPS that I was out with that day. And you can see that the coordinates match what I put up here. Yeah, it's kind of interesting. GPSs use satellites, and flat earthers don't believe in the existence of satellites, yet I'm still getting readings. That's funny. Anyway, I'll continue. Okay, this is how I knew I had ideal conditions. So I was driving south on US 41, and I stopped because I was looking over Keweenaw Bay, and I'm like, you know what? I'm going to give this a go. So I turned around, stopped, I checked my vehicle temperature, which gauges external air temperature. I got 36 degrees Fahrenheit. I got on my phone, checked the weather, 36 degrees. This is just to show you the weather for the rest of the week. And then I went to scroll down some more, and I got a humidity of 61%, which isn't low, but it's not really high. And considering the fact I had high cloud cover, it's not really going to affect anything. The high cloud cover was another good indicator that I had ideal conditions because I don't have the sun glaring down on the water to create mirages. And my visibility was maximum of about 10 miles. Official weather data here from my iPhone. It's a 6S. It's whatever weather app comes on with the phone. So these conditions are good in and of themselves, but they're not ideal. I need one other thing to confirm ideal conditions, and that's coming up next. So I got on my phone and I went to the NOAA Great Lakes Coastal Forecasting System to see what the surface water temperature was. Okay, now there's a station here. This red box is this red box. So it's a good clip north of me, but not too far north. I'm at the star right here about. Here's that jutting out peninsula. And the surface temperature was 40.5 degrees Fahrenheit. That means I had a difference of surface water temperature and air temperature of only 4.5 degrees. And actually, if you look here, it's shaded a little bluer than it is at the actual station. So it could have been actually closer to my actual air temperature, the surface water, but we'll just go with 40.5 degrees since that's the official reading. So my surface water temperature and my atmospheric temperature are really close to each other, okay? And I had high cloud cover on top of that, all right? And I had good visibility, that 10 miles visibility, okay? So that's what I mean by I had ideal conditions, because those kind of conditions are going to make mirages non-existent. I'm not going to have any superior mirages. I'm not going to have any inferior mirages. What I see in the distance, I should be able to shoot an accurate azimuth to, okay? And looming is also kept to a minimum under these conditions. What I did was I took my Brunton compass, here it is on my lap, just to show you what it is. And these things are not cheap, they're about $450 a piece, but they are great tools. We use them in geology all the time. This is the degrees of a circle. Notice this is 90, 90, 90, 90. This is a quadrant one. You can get them in 360 degrees. It's just from geology. For geologic purposes, this quadrant setup is easier to work with. And we're going to be working off the northeast quadrant anyway, so I don't need to say things like, if you look here, I'm facing south 42 degrees east, south 42 degrees east. When this thing was sitting on my lap, roughly. I mean, my bubbles aren't level, but that's close. I won't need to say things like south 42 east. I could just say, since we're in the northeast quadrant, I could just say 42 degrees. Okay, and that's what I'm going to say. All right, now the Brunton is a beautiful tool for many reasons. If you notice here, for one thing, the east is on the left side, the west is on the right side. You might say, that's backwards. No, it isn't. Unlike lensetic and cheap compasses, which have the east on the right side, The purpose of this compass is to actually take the physical reading from this arrow from which you are facing. And if this was west and east, that wouldn't happen. Okay, so this compass is made to compensate for all those little things other compasses don't, like true direction, and other things which I'm going to get to here in a minute. But basically, when you're holding this compass taking measurements, okay, you have this is your inclinometer, and as you can see here, I set it at 0. Now we go back to here, set it 0. What that does is this actually moves. There's a lever on the back, so if I have this on a planar surface that's plunging or dipping down slope, I can get an actual degree dip when this levels out. I'm not going to get too much into how it works. I just want to point some basic things out. But from horizontal surface, you want it set at 0, because what that'll do is you know your level if this bubble is in the middle and this bubble is in the middle. So you have 2 leveling bubbles in this thing. Okay? Like I said, here it is again. I had it set at my inclinometer set at 0. Now the Brunton does another beautiful thing that other compasses do not. It compensates for magnetic declination, because magnetic north is almost never true north from where you are. So what I did was I got on my phone and I got my magnetic declination for my location, and it's minus 4.09 degrees or west 4.09 degrees. So what I did is I turned my compass, the degree part here, you can see here's 0, this is north, the star means north. So 1, 2, 3, 4. I set it to 4 degrees. Obviously it's not going to do the 0.09. Brunton is generally accurate to within half a degree, which is a lot better than any other compass. So I compensated for my magnetic declination, which means if I take a reading off of this, my azimuth in degrees is going to be from true north, not magnetic north. Okay? And here's what it looks like just stretched out. This actually is, I took some video when I was out there, but the thing was, trying to shoot a video with your phone, since this was impromptu and taking measurements didn't work out too well, so I took a few screenshots to show you that yes, I actually was there. This is Keweenaw Bay, this is that jutting out peninsula, that's that long stretched out peninsula, okay, of the Keweenaw, of where we're looking. Now, but the point of this is to show you the Brunton. Now you can shoot a Brunton reading from several locations. The 2 most popular are from eye level, which I did, and it ended up working out just fine. Or you can hold it on your stomach, because this part is the half that closes it, and on this surface, you can't see it here, is a mirror. So what you can do is you can set it up to shoot things using this, and this is a nice little sight, and this is your back sight. If you wanted to shoot from your stomach, you fold the mirror up, you push this down, and you can still get a reading by using the mirror. But I wanted to do eye level, so there would be no, well, you didn't shoot it from eye level statements about this. Now, this is a screenshot from me looking out across Keweenaw Bay. This, unfortunately, was the best screenshot I could get from that video. As you can see, there's clouds, they're higher up. It's clear from here to that. This is that jutting out peninsula. Now I actually took measurements from here and the southern end. The southern end has a good marker, the northern end has a clear marker, and you can kind of see the shore here a little bit, so you know you can see some land. And so I took 2 measurements off the jutting peninsula to get my control points, and then I took one from as far as I could see. Now if you notice out here, it's, I don't know, I hope this is good enough to see. It's better for me to see on my TV, but these are all trees, and then they just kind of peter off in the distance. You don't see the rocky shore, okay? And that's significant, right? Oh, and this line here is my horizon, okay? Now here's 2 of the 3 azimuths I shot. I didn't have, my screen wasn't wide enough to include all 3 measuring points, so I just went with this one. I shot an azimuth to the north end of the jutting out peninsula. I got 71.5 degrees, and I shot an azimuth out as far as I could see, which I got 69 degrees. And then I shot one to the southern end over here and took a measurement. I'll cover that later. I did include it, just not visible in the picture. Okay, so this is that north azimuth I took. I'm standing here. This is my line. From Google, I should have been able to see this point. Now remember, I got an azimuth of 71.5 degrees. Google gives me this angle, I should say, as 70.4 degrees. Okay, so my margin of error, I had to calculate one just for a reference point. I used 360, a complete circle. There's my calculation. I got 0.31%. Okay, so that's less than 0.5% of a margin of error. And I could see 5.07 miles. 5.07 miles is this yellow line from where I was to right there. Okay, next point. The southern tip. I zoomed in a little bit here more because there's a good marker here, but you can't really see it on this picture anyway. But so there I was, shot my azimuth to the southern end of the jutting out peninsula. I got 88 degrees, okay? Google, to that point that I could see on the southern end, gave me an azimuth of 89.6 degrees from north, okay? So I did the same thing again, calculated margin of error using 360 degrees. I got 0.44% margin of error. And this yellow line right here, that's a distance of 3.65 miles, okay? One more point. Now, I shot an azimuth of 69 degrees. So I put that into Google. Now this is not a control point. I shot these two. I got low margins of error. So there's no reason to think that this point is any less accurate than the ones I shot here. But I shot an azimuth of 69 degrees. And if I put 69 degrees into Google, that means I could see right to this point for a distance of 8.99 miles, or roughly 9 miles. Now that's significant, okay, because as I will get into, I should have been able to see a lot further on a flat Earth since I had ideal atmospheric conditions, and I couldn't. So this is a strong indication that the Earth is not flat. All right. Okay, according to a flat Earth model, I should have been able to see this tip right here, which gives me a Google azimuth of 62 degrees. I shot a maximum sight azimuth of 69 degrees. And I forget what the exact point is, so that means I saw it right here. Okay, so this distance is 17.41 miles. Okay, now I calculated just like I did my other points, a margin of error, and I got 1.94%. Okay, now my control points that I measured here and here from the jutting out peninsula gave me margins of errors of less than 0.5%. So which means this is outside of my margin of error and I was not looking at this point. There's no reason to think my sight azimuth of 69 degrees was any less accurate than my other 2 points since my conditions were identical. I shot the other 2, then I shot the third one, all continuously in a row. And I had the first 2 with my control points. Okay, so I did not see out 17.41 miles at an azimuth of 62 degrees. Now, what's my distance to the horizon? Well, that I had to go online, and this part here is just reference for this. This is a European site, so they have commas instead of decimals. But my height from what I was standing upon to my eye level from Lake Superior, which has an average elevation of about 600 to 602 feet above sea level, well, I was 22 feet above that at eye level. Okay, so I can look at this chart and see, well, I'm between here and here. Well, there's an actual calculator you can use to your distance to the horizon right here, and it is 5.7 miles, okay? But I saw 9 miles. That means I could see 1.6 times further than predicted. Well, what would make me see that further out? I mean, if the Earth was round, should I only be able to see it at 5.7 miles? No, and I'll get into that later in the video. But, however, that is still nowhere near what Flat Earth model predicts I should be able to see. Now, Flat Earth models vary, and basically, no, there is no exact consensus because their entire argument essentially boils down to, well, it looks flat. And I'm going to get into perception is not reality later. So I just picked one. And I picked a more conservative one. I went to Flat Earth Wiki, whatever that is. And if you see here, you can read all this if you want. Not going to stop you. They give, at sea level, the average air density is 1.225 kilograms per meter cubed. I don't know where they got this number from. They don't never show any equations. There's no equations here at all, just results. And no processes or notes either. So, remember what I said about the cylinder and the cube? But anyway, just taking their word for it, this sort of density will allow a viewing distance of around 25 miles across the horizon. I didn't see 25, remember I saw 9, okay? In New York, pollution and humidity are such at high levels that viewing distance is limited to 15 miles. Well, I was in the Upper Peninsula of Michigan, more than 600 feet above mean sea level, and the UP is not known for its atmospheric pollution. So I'm going to go with the 25 miles. But even if I went with the 15, I still didn't see that far. Okay. Now they even get into something here. At higher altitudes, the air density drops sharply, allowing the viewer to see faraway lands before they are obscured by a blue-white sky. I don't know what blue-white exactly means. I assume they think that the horizon looks whitish. I don't know. It is for this reason that an observer standing on Mount Everest can see other mountains hundreds of miles away. Such pristine conditions are rare on Earth, yet they don't define pristine or rare. However, only existing at high altitudes in frigid environments. Now, like I said, I was above 600 feet above mean sea level, and I doubt they would consider that high altitude, since Lake Superior was my baseline. But they also don't define what high altitude is. And they also say frigid environments. They also don't define that. My concept as being someone who visits the Upper Peninsula and Ontario a lot, I have a totally different concept of what frigid is than someone living in Texas or the Caribbean. But I was near freezing, water and air temperature. So that should make that I should be able to see 25 miles on a flat Earth, no problem. But I didn't. Okay, now, so what I did was I drew a circle with a 25-mile radius. Okay, here's my circle. This line is 25 miles. If you don't believe me, you can go to Google Earth and plug in my GPS coordinate and draw the line yourself. This is the center. That's my point. Okay, now, if something else too, I did try to look for other points for control points and reference points, but I couldn't see them. The closest one to me that makes a good one is White City Park, which has an elevation of 609 feet above mean sea level. That's 9.1 miles away. Okay, now that's lower in elevation than me, but on a flat Earth, I should have been able to see it, no problem. I couldn't see it at all. I could not see this point at all. Okay? And it was just past where I actually saw, so it should be visible. But someone might sit there and say, well, that's too low, much lower than you. Okay, fine. So up here is Traverse Island. Elevation 648 feet above mean sea level, 18.2 miles away. That's still well within my flat Earth model of a radius of 25 miles, and I could not see it. Okay, so I mean, sitting there and say, well, you can't see further out because atmospheric particles, blah blah blah. Yet they never tell you what those particles are or how they work. Could be obscuring my line of sight. I didn't have that based on their wiki page. Okay. So, why couldn't I see these? Well, they were past my horizon. They were past my line of sight and way past my horizon. Not only were they past my horizon, but they did down below, further away, so I couldn't see them. Okay? So, my flat Earth distance, I should have been able to see 17.4 miles to the tip of that peninsula, that long peninsula. I didn't. Okay? Round Earth prediction says 5.7 miles to the horizon. I actually saw 9 miles. The difference between round Earth prediction and what I actually saw is 3.3 miles. Okay, the difference between flat Earth prediction and actual is 8.4 miles. That is more than twice, okay, the round Earth prediction. That is off by a huge margin, okay? It's off by almost what I actually did see, 9 miles. So that's a huge margin of error, and really doesn't hold and doesn't really do much for the flat Earth model. Now, you might be wondering, well, I said I was going to get into why I could see 9 miles out instead of just 5.7 to the horizon. Hold on, let me go back. I'm going to show you that picture again. Okay. This is why. My horizon was at 5.7 miles, okay? Now, if you look here, I said these are trees. These tall pine trees in the Upper Peninsula can be 60 to 100 feet tall. So just take an average of 80 feet, that means they would be 80 feet higher than my eye level, because the land surface here is about the same height as my eye level. That's 622. So you add another 80 feet above that, it's no wonder I could see further. But as you can tell, the trees kind of just peter off in the distance, all right? Indicating that there's some curvature going on here. Because remember, I don't have any atmospheric interference, all right? Okay, so that's why I could see them 9 miles, because I was actually able to see 80 feet above where I was standing. So of course I'm going to be able to see further out, all right? But I still didn't see the tip that is predicted by a flat Earth at 17.4 miles, because that was way past my horizon. So the flat Earth model doesn't hold up here. So the round Earth prediction, and from my observations, holds up. Okay, it makes a lot more sense than a flat Earth. And I'm going to show you something. I'm going to show you how perception is not reality, and I am not kidding when I basically say the only thing flat earthers can agree on is that it looks flat. That's their argument. Okay, so it looks flat. So what? Big deal. Who cares, right? Okay. I am Crazy Cat Man. I have 3 cats. This is a shadow of my cat. You know, on the rug, it looks like my cat, you know, within this narrow field of view for my point. Here's his little ears, here's his back, here's his tail, you know, here's his front. It's my cat, right? No, it's not. It's my book bag. Okay? And this is just one of those things showing you that just because something looks like something doesn't mean that's what it is. All right? You need to confirm that what this shadow is. Well, what's casting the shadow? Yeah, it looks like a cat, but if I zoom back, pull out, stand further away, it's a book bag. It's not even a living thing. Okay, so yeah, perception is not always reality, okay? Just because something looks as it is doesn't mean your eyes are perceiving it correctly. And plus, any preconceived notion that you may have about the world around you doesn't matter, because reality is absolutely under no laws to conform to your preconceived biases. So, in a nutshell, the Earth is round. Okay? It's not flat. People just need to learn to get over it, okay? I hope that video was thorough enough for you, and I hope it explained a lot. I tried to go through it a lot quicker than I probably should have, but there it is, and I hope you got something out of it.